Position and displacement. Position, path length, and displacement. Motion is defined as change in position of an object with time. In order to specify position, we use a reference point and a set of axes. It is convenient to choose a rectangular coordinate system consisting of 3 mutually perpendicular axes labeled X, Y, and Z axis. Point of intersection of these 3 axes is called origin, O, and serves as the reference point. The coordinates x, y, z of an object describe the position of the object with respect to this coordinate system. To measure time, we position a clock in this system. This coordinate system, along with a clock, constitutes a frame of reference. If one or more coordinates of an object change with time, we say that the object is in motion. To describe motion along a straight line, we can choose an axis, say x-axis, so that it coincides with the path of the object. We then measure the position of the object with reference to a conveniently chosen origin, say O. Positions to the right of O are taken as positive and to the left of O as negative. Description of an event depends on the frame of reference chosen for the description. For example, when you say that a car is moving on a road, you are describing the car with respect to a frame of reference attached to you or to the ground. But with respect to a frame of reference attached with a person sitting in the car is at rest. Path length. Consider the motion of a car along a straight line. We choose the x-axis such that it coincides with the path of the car's motion and origin of the axis as the point from where the car started moving. That is, the car was at x is equal to 0 and t is equal to 0. Let P, Q, and R represent the positions of the car at different instants of time. Consider 2 cases of motion. In the first case, the car moves from O to P. Then, the distance moved by the car is OP is equal to plus 360 meters. This distance is called the path length traversed by the car. Distance is the actual path length traveled by a body. In the second case, The car moves from O to P and then back from P to Q. During this course of motion, the path length traversed is OP plus PQ is equal to plus 360 meters plus 120 meters is equal to plus 480 meters. It is very important to understand that path length is a scalar quantity that has magnitude only and no direction. Displacement. Now let us understand about displacement. Displacement is the actual change in the position of the body. Let us take an example. Let x1 and x2 be the positions of an object at time t1 and t2. Then its displacement, denoted by delta x in time delta t is equal to t2 minus t1, is given by the difference between the final and initial positions. Delta x is equal to x2 minus x1. We use the Greek letter delta to denote a change in a quantity. x2 is greater than x1. Delta x is positive. And if x2 is less than x1, delta x is negative. Displacement has both magnitude and direction. Such quantities are represented by vectors. For example, displacement of the car in moving from O to P. OP is equal to delta x is equal to x2 minus x1 is equal to plus 360 meters minus 0 meters is equal to plus 360 meters. The displacement has a magnitude of 360 meters and is directed in the positive x direction, as indicated by the positive sign. Similarly, the displacement of the car from P to Q is 240 meters minus 360 meters is equal to minus 120 meters. The negative sign indicates the direction of displacement. The magnitude of displacement may or may not be equal to the path length traversed by an object. Motion of an object can be represented by a position-time graph. Such a graph is a powerful tool to represent and analyze different aspects of motion of an object. For motion along a straight line, say x-axis, only x-coordinate varies with time, and we have an xt graph. Let us first consider the simple case in which an object is stationary. For example, say a car standing still at x is equal to 40 meters. The position-time graph is a straight line parallel to the time axis. If an object moving along the straight line covers equal distances in equal intervals of time, it is said to be in uniform motion along a straight line. The motion of a car that starts from rest at time t is equal to 0s from the origin O and picks up speed till t is equal to 10s and thereafter moves with uniform speed till t is equal to 18s. Then the brakes are applied and the car stops at t is equal to 20s and x is equal to 300 meters. Average velocity and average speed, Part 1. Average velocity is defined as the change in position or displacement delta x divided by the time intervals delta t in which the displacement occurs. V bar is equal to x2 minus x1 upon t2 minus t1 is equal to delta x upon delta t, where x2 and x1 are the positions of the object at time t2 and t1 respectively. The SI unit for velocity is meter per second. Like displacement, average velocity is also a vector quantity. Consider the motion of the car as shown here. As seen from the plot, the average velocity of the car between time t is equal to 5s and t is equal to 7s is V bar is equal to x2 minus x1 upon t2 minus t1 is equal to delta x upon delta t is equal to 27.4 minus 10 upon 7 minus 5 is equal to 17.4 upon 2, 8.7 meter per second. Geometrically, this is the slope of the straight line P1, P2, connecting the initial position P1 to the final position P2. The average velocity can be positive or negative depending upon the sign of the displacement. It is 0 if the displacement is 0. Here you can see an xt graph for an object moving with positive velocity. Moving with negative velocity. Average velocity, as defined earlier, involves only the displacement of the object. But the magnitude of displacement may be different from the actual path length. To describe the rate of motion over the actual path, we introduce another quantity called average speed. Average speed is defined as the total path length traveled divided by the total time interval during which the motion has taken place. Average speed is equal to total path length upon total time interval. But it does not tell us in what direction an object is moving. Thus, it is always positive, in contrast to the average velocity, which can be positive or negative. Average velocity and average speed, Part 2. Let us now look at an example. A car is moving along a straight line, say OP. It moves from O to P in 18s and returns from P to Q in 6.0s. What are the average velocity and average speed of the car? In going from O to P and from O to P and back to Q, first case, from O to P. Average velocity is equal to displacement upon time interval. V bar is equal to 360 meters upon 18s is equal to 20 meter per second. Average velocity is equal to 20 meter per second. Average speed is equal to path length upon time interval is equal to 360 meters upon 18s is equal to 20 meter per second. Average speed is equal to 20 meter per second. Thus, in this case, the average speed is equal to the magnitude of the average velocity. Second case, from O to P and back to Q. In this case, average velocity is equal to displacement upon time interval is equal to OP minus PQ upon T is equal to plus 240 meters upon 18 plus 6s is equal to 1.0 meter per second. Average velocity is equal to 1.0 meter per second. Average speed is equal to path length upon time interval is equal to OP plus PQ upon T is equal to 360 plus 120 meter per 24 second is equal to 20 meter per second. Average speed is equal to 20 meter per second. Thus, in this case, the average speed is not equal to the magnitude of the average velocity. This happens because the motion here involves change in direction, so that the path length is greater than the magnitude of displacement. This shows that speed is in general greater than the magnitude of the velocity. Instantaneous velocity and speed. The average velocity tells us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at different instants of time during that interval. For this, we define instantaneous velocity, or simply velocity v at an instant t. Let us further understand the concept with an example. The position of an object moving along x-axis is given by x is equal to a plus bt square, where a is equal to 8.5 meters, b is equal to 2.5 meter per second square, and t is measured in seconds. What is its velocity at t is equal to 0 second and t is equal to 2.0 second? What is the average velocity between t is equal to 2.0 second and t is equal to 4.0 second? Answer. In notation of differential calculus, the velocity is v is equal to dx upon dt is equal to d upon dt into a plus bt square is equal to 2bt is equal to 5.0 t meter per second. At t is equal to 0 s, v is equal to 0 meter per second, and at t is equal to 2.0 s, v is equal to 10 meter per second. Average velocity is equal to x into 4.0 minus x into 2.0 upon 4.0 minus 2.0 is equal to a plus 16b minus a minus 4b upon 2.0 is equal to 6.0 into b is equal to 6.0 into 2.5 is equal to 15 meter per second. Note that for uniform motion, velocity is the same as the average velocity at a particular time. Also, instantaneous speed, or simply speed, is the magnitude of velocity. Kinematic equations for uniformly accelerated motion. Part 1. For uniformly accelerated motion, we can derive some simple equations that relate displacement x, time taken t, initial velocity v naught, final velocity v, and acceleration a. Equation v is equal to v naught plus a into t gives a relation between final and initial velocities v and v naught of an object moving with uniform acceleration a. This relation is graphically represented as shown here. The area under this curve is area between instants O and T is equal to area of triangle ABC plus area of rectangle OACD, which is equal to 1 by 2 V minus V naught T plus V naught T. You know that the area under the VT curve represents the displacement. Therefore, the displacement x of the object is x is equal to 1 by 2 v minus v naught t plus v naught t. V minus v naught is equal to a into t. X is equal to 1 by 2 at square plus v naught t. X is equal to v naught t plus 1 by 2 at square. X is equal to v plus v naught by 2t is equal to v bar t. V plus v naught by 2 is equal to v bar. For constant acceleration only. Kinematic equations for uniformly accelerated motion. Part 2. Previous equation means that during the constant acceleration, the object has undergone displacement x with an average velocity equal to the arithmetic average of the initial and final velocities. From equation 1, t is equal to v minus v naught by a. Substituting this in equation x is equal to v plus v naught t by 2 is equal to v bar t. We get x is equal to v bar t is equal to v plus v naught by 2 into v minus v naught by a is equal to v square minus v naught square by 2a. V square is equal to v naught square plus 2ax. Thus, we have obtained three important equations. V is equal to v naught plus at. X is equal to v naught t plus 1 by 2 at square. V square is equal to v naught square plus 2ax. Connecting five quantities v naught, v, a, t and x. These are kinematic equations of rectilinear motion for constant acceleration. Equations of motion using the method of calculus. We know that instantaneous acceleration a is equal to limit delta t tends to 0, delta v by delta t is equal to dv by dt. A is equal to dv by dt. dv is equal to a dt. Integrating both sides, we get integral v naught to v dv is equal to integral 0 to t a dt is equal to a integral 0 to t dt. A is constant. V minus v naught is equal to at. V is equal to v naught plus at. Further, v is equal to dx by dt. Dx is equal to v dt. Integrating both sides, integral x naught to x dx is equal to integral 0 to tv dt. Substituting v is equal to v naught plus at, we get integral 0 to t v naught plus at dt x minus x naught is equal to v naught t plus 1 by 2 at square. X is equal to x naught plus v naught t plus 1 by 2 at square. We can write a is equal to dv by dt is equal to dv by dx. Dx by dt is equal to v dv by dx. Or v dv is equal to a dx. Integrating both sides. Integral v naught to v dv is equal to integral x naught to x a into dx. V square minus v naught square by 2 is equal to a into x minus x naught. V square is equal to v naught square plus 2ax minus x naught. So we can find the equation of motion using calculus. The advantage of this method is that it can be used for motion with non-uniform acceleration also. Acceleration. The velocity of an object, in general, changes during its course of motion. The rate of change of velocity with time is a constant of motion for all the objects in free fall. We find that the change in velocity with distance is not constant. It decreases with the increasing distance of fall. This leads us to the concept of acceleration as the rate of change of velocity with time. The average acceleration a over a time interval is defined as the change of velocity divided by the time interval. So, a bar is equal to v2 minus v1 upon t2 minus t1 is equal to delta v upon delta t, where v2 and v1 are the instantaneous velocities or simply velocities at time t2 and t1. Acceleration is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of velocity versus time, the average acceleration is the slope of the straight line connecting the points corresponding to v2 t2 and v1 t1. Instantaneous acceleration. The acceleration at an instant is defined as the limit of the average acceleration as the time interval delta t becomes infinitesimally small. A is equal to limit as delta t tends to 0, delta v by delta t is equal to dv by dt. The acceleration at an instant is the slope of the tangent to the vt curve at that instant. Since velocity is a quantity having both magnitude and direction, a change in velocity may involve either or both of these factors. Acceleration, therefore, may result from a change in speed or magnitude, a change in direction, or changes in both. Position time graphs. Like velocity, acceleration can also be positive, negative, or zero. Position time graphs for motion with positive, negative, and zero acceleration are shown here. It should be noted that the graph curves upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. Velocity time graphs. Let us see how velocity time graph looks like for some simple cases. A. An object is moving in a positive direction with a positive acceleration. For example, the motion of the car in between t is equal to 0s and t is equal to 10s. B. An object is moving in positive direction with a negative acceleration. For example, the motion of the car in between t is equal to 18s and 20s. C. An object is moving in negative direction with a negative acceleration. For example, the motion of a car moving from O in negative x direction with increasing speed. D. An object is moving in positive direction till time t1 and then turns back with the same negative acceleration. For example, the motion of a car from point O to point Q till time t1 with decreasing speeds and turning back and moving with the same negative acceleration. Note, an interesting feature of a velocity time graph for any moving object is that the area under the graph represents the displacement over a given time interval. We can see that it is true for a simple case of an object moving with constant velocity u. Its velocity time graph is as shown here. The vt curve is a straight line parallel to the time axis, and the area under it between t is equal to 0 and t is equal to t is the area of the rectangle of height u and base t. Therefore, area is equal to ut, which is the displacement in this time interval. Relative velocity. In this module, let us understand the concept of relative velocity. We are all familiar with the experience of traveling in a car and being overtaken by another car moving in the same direction as we are. Since the second car overtakes the first car, the second car is traveling faster than the first car. So a person sitting in the first car will find the second car moving with some speed. Now let us take the case of a person standing on the ground watching both the cars move. Let the person sitting in the first car report a speed of the second car as x. Let the person standing on the ground report the speed of the second car as y. We will find that y is always greater than x. Now let us take another scenario. In this case, both the cars are moving with the same speed with respect to the ground. Then, to the person sitting in the first car, the second car will not be moving at all. That is, relative to the person sitting in the first car, the second car will not be moving. However, to a person standing on the ground, the second car will be moving with a speed. To understand such observations, we now introduce the concept of relative velocity. Two objects moving uniformly along the x-axis. Consider two objects A and B moving uniformly with average velocities VA and VB in one dimension, say along x-axis. If XA 0 and XB 0 are the positions of the objects A and B, respectively at time t is equal to 0, their positions xat and xbt at time t is equal to t are given by xat is equal to xa0 plus vat. Xat is equal to xb0 plus vbt. Then, the displacement from object A to object B is given by xbat is equal to xbt minus xat. xba is equal to xb0 minus xa0 plus vb minus va into t. The above equation is easily interpreted. It tells us that as seen from object A, object B has a velocity Vb minus Va. Because the displacement from A to B changes steadily by the amount Vb minus Va in each unit of time. We say that the velocity of object B relative to object A is Vba is equal to Vb minus Va. Similarly, velocity of object A relative to object B is Vab is equal to Va minus Vb. Vba is equal to minus Vab. Speeds observed by the moving and stationary persons. Now let us go back to the earlier example. Suppose the first car was moving with speed x and the second car was moving with speed y, where y is more than x. Then, the speed of the second car to a person in the first car that is, moving with speed x will be y minus x from the previous discussion. However, speed of the second car to a person standing stationary on the ground will be y minus 0 or y, as the person is standing still. Hence, we can clearly see that there is a distinction in the speeds observed by the person sitting in the car and the person standing on the ground. Now let us consider some special cases. A. If VB is equal to VA, VB minus VA is equal to 0. Then, XBT minus XAT is equal to XB into 0 minus XA into 0 plus VB minus VA into T becomes XBT minus XAT is equal to XB into 0 minus XA into 0. Therefore, the two objects stay at a constant distance xb into 0 minus xa into 0 apart, and their position time graphs are straight lines parallel to each other. The relative velocity VAB or VBA is 0 in this case. Two objects moving with different velocities. Now let us take the case of two objects moving with different velocities. That is, if VB is greater than VA, VA minus VB is negative. One graph is steeper than the other, and they meet at a common point. For example, suppose VB is equal to 20 meters per second and XB into 0 is equal to 10 meters and VA is equal to 10 meters per second. XA into 0 is equal to 40 meters. Then, the time at which they meet is t is equal to 3s. At this instant, they are both at a position xb into t is equal to xa into t is equal to 70 meters. Thus, object B overtakes object A at this time. In this case, VAB is equal to 10 meters per second minus 20 meters per second is equal to minus 10 meters per second is equal to minus VBA. Suppose VA and VB are of opposite signs. For example, if an object A is moving with 20 meters per second, starting at xa into 0 is equal to 10 meters, and object B is moving with minus 10 meters per second, starting at xb into 0 is equal to 40 meters, the two objects meet at t is equal to 1 second. The velocity of B relative to A VBA is equal to minus 10 minus 20 meters per second is equal to minus 30 meters per second is equal to minus VAB. In this case, the magnitude of VBA or VAB is equal to 30 meters per second, which is greater than the magnitude of velocity of A or that of B. In this case, to a person sitting in either of the two cars, the other car seems to go very fast. Acceleration in a freely falling body. Free fall, neglecting air resistance. An object released from the height of the Earth's surface is accelerated downward under the influence of the force of gravity. If air resistance is neglected, the object is said to be in free fall. The magnitude of acceleration due to gravity is represented by g. If the height through which the object falls is small compared to the Earth's radius, g can be taken to be constant, equal to 9.8 meter per second square. Free fall is thus a case of motion with uniform acceleration. We assume that the motion is in y direction. More correctly, in minus y direction, because we choose upward direction as positive. Since the acceleration due to gravity is always downward, it is in the negative direction, and we have A is equal to minus g is equal to minus 9.8 meter per second square. The object is released from rest at y is equal to 0. Therefore, v naught is equal to 0, and the equations of motion become v is equal to 0 minus gt is equal to minus 9.8 t meter per second, y is equal to 0 minus 1 upon 2 gt square is equal to minus 4.9 t square meter. V square is equal to 0 minus 2gy is equal to minus 19.6 y meter square per second square. These equations give the velocity and the distance traveled as a function of time, and also the variation of velocity with distance. relations of acceleration, velocity, and distance with time have been plotted in figure A, B, and C. Galileo's law of odd numbers. Galileo's law of odd numbers states that the distances traversed during equal intervals of time by a body falling from rest stand to one another in the same ratio as the odd numbers beginning with unity. Let us see the proof of this law. Since initial velocity is 0, we have y is equal to minus 1 upon 2gt square. Using this equation, we can calculate the position of the object after different time intervals 0, tau, 2 tau, 3 tau, which are given in second column of the table as shown here. If we take minus 1 upon 2g tau square as y0, the position coordinate after first time interval tau, then the third column gives the positions in the unit of y0. The fourth column gives the distances traversed in successive tau s. We find that the distances are in the simple ratio 1 is proportionate to 3, is proportionate to 5, is proportionate to 7, is proportionate to 9, is proportionate to 11 as shown in the last column. And students, for your knowledge, this law was established by Galileo Galilei, 1564 to 1642.